Yeah. Today we're going to talk about Fourier transform. So we'll start with first 1D continuous Fourier transform, and then we'll define the discrete version. Then we'll go to 2D continuous version, and then discrete Fourier transform in 2D, and then we'll see how we can use this Fourier transform to do some some filtering, and we'll see what it actually means, and what Fourier basis functions mean and all. Okay. Uh, so let's first start with 1D discrete for 1D Fourier transform. Let's say we are given so let's say we are given a signal x. Forget this definition for now. That it's discrete, and then the Fourier transform is nothing but you take an integral of this function over a set of harmonics, and the integral over it is defined, which is parameterized by psi, which we call it as spatial frequency. If it's 2D, and it's just frequency if it's 1D. Um, then we can write the discrete Fourier transform as xk is just by removing this integral, and just by summing it from minus infinity to infinity, and since we wrote this x1 x2, since our x was discrete, so you multiply with a discrete set of coefficients, and that is the discrete Fourier transform. So in here, instead of instead of applying from minus infinity to infinity, you just take divide the coefficient by n, so you get all the harmonics within 2 pi, because pi plus k is equivalent to k. So you can rewrite it this way. So let's see some examples. So we want to generate a sine wave, or any wave for that matter. Let's say we want 10 cycles within a second, and we want 100 samples like that within the whole thing. So let's generate some time samples. So so it's we basically generated 200 samples for 2 seconds. And then we'll see and then we'll plot the sine curve. So if you observe, this has a frequency of this has basically it's between 0 to 2, and it has 10 waves within a second, and you have totally 100 points which span through this curve, right? So here, I mean, we can implement ourselves this Fourier transform as by maintaining this x as a vector, and you can create a vector of all these harmonics, and you can just do a dot product, and that will give you the Fourier transform. So in 1D case it's okay, but when you go into 2D and beyond, so it's not really it's ideally it's O of n square, the number of operations, but there are some implementations which provide it even faster. They have a O of n log n implementation. So we won't implement it. We won't implement the Fft ourselves, and we use it from the SciPy Fft pack. Okay, but this is not the fastest. There's another package in Python which is faster than Sanketh. So just for convenience, we're using this. So if you take the Fourier transform of so what do we expect if we take a Fourier transform of this? We expect a single frequency in the frequency domain. So and basically that's what we see. So these both are equivalent because it's symmetric over the frequency of 10 it's also equal to C frequency of minus 10. So I mean, I'll tell you what this curve means. So first we took the Fourier transform here. So we can even plot it. Yeah. So we get something like this when we plot it, but we can't really see what is the frequency that we're looking for. So there's this other function called Fft frequency. So basically you multiply that, so you give it to that how many points, how many bins you're having in the you're having in the how many bins of frequency you're giving it, and it will tell you where exactly the which frequency does this peak align to. So here we can see that it's at 10 and minus 10. So yeah, sure, yeah, this one. Okay. This x is the yeah. No, at the capital X is the Fourier transform of small x. Yeah. Let's see an example which Alex mentioned in the class. So we built a delta function. So basically, you take 20 a 20 dimension vector, and you just put 1 at one point. So what do we expect to see? We saw in the class that the Fourier transform of a delta function is just 1, right? So let's see what we get. So this is the delta function. So you have only 1 at a point, and so this is the, so if you take the Fourier transform, so what we're doing, we're just taking a Fourier transform of x, and we're plotting the absolute value. So we're plotting the absolute value. So so we see that the delta function uses all the coefficients in the harmonics to build that single peak. So that, which is what we observed even in the class, right? So okay. Yeah, so let's build another function which is also interesting. So so let's consider let's consider a box function where you only few elements in between are ones and the rest are zeros. So let's see what we get, and then we'll derive mathematically how I mean from the definition of Fourier transform what you're supposed to get, and we see if they align or not. So okay, the first plot shows you the absolute the real value of the Fourier transform, which is this function which has this is called as a Sinc function, which is I'll briefly show you what it actually is. And this is the amplitude. So you have a dampening. You have very high frequency. You have very high amplitude in the center, and it slowly dampens beyond. So let's see how we get it. So so our function. This is the continuous version of the Fourier transform. So when we build a box function, it means that you have from an interval of minus t to t, the value of the h of x, the function is 1, and the rest is 0. So so since we if you put this in, basically the 0 part goes away, and you remain with minus t to t, and you have to take the integral of this, right? So it's a simple integral, and then you divide it. So you just take this minus 2 pi I by cx into the c into the denominator, and then you end up with something like this. So it can be written as it's a form sine pi x by x. So the plot of sine pi x by x, it's called a Sinc function, which looks like this. So this is also important because the box filters are quite common in 1D signal processing. So they actually design the box filters according to what level of dampening do you need. So it can be implemented analog because it's block, and you can get what characteristics you want in the signal by just choosing these peaks. Okay. So so now. So now we come to an important question, like is it when does Fourier transform exist in continuous case? So usually we think that it exists all the time, but because whenever we input something to a SciPy function, you get something out. But in the continuous case, it's defined only when f of x is absolutely integrable, which means that when you take when you take an L1 norm of integral of x, it should dampen when you sum to infinity. It shouldn't cross infinity, so it should have some kind of a damping. It should be less than infinity. So that's why whenever you take any discrete functions, they eventually any sum of countably infinite numbers is still less than infinity. So that's why we always get the Fourier transform for functions which, for example, if you take a sine function which is 0 in the negative and 1 in the positive, so it's the Fourier transform of sine in the continuous version is not very straightforward to get, because it doesn't, when you integrate it to infinity, it goes to infinity. It doesn't go below. So you kind of there's some ways which you can get the Fourier transform of that, but in continuous version it's also but it exists, right? But these are sufficient conditions. They are not necessary. So if such a function, if you have a function which has this behavior, either absolutely integrable or square integrable, so then it means that that Fourier transform of such functions exists in continuous space. So now let's go to 2D Fourier transform. So when you have so let's say you have the continuous version of the Fourier transform is defined like this. So the integrals can be, of course, exchangeable because the integral is linear. So f of xy is our image, and so if you want to apply the Fourier transform, so you just multiply with this and take an integral over x and y. So it's a function of u and v are called spatial frequencies. U is along x and v is along y. So depending on how they commute with x and y, so v commutes with y, so it's spatial frequency along y. So for this, for this you can define the discrete version of Fourier transform as a double summation of 0 to n minus 1. Exactly the same as how we defined in the discrete case, except you have two summations. That's it. So now let's generate some toy images and see how Fourier transform changes them. So we're generating a box. Just a second, I'll show you. So what do you expect the Fourier transform of this to look like? Yeah. So it's like yeah. So yeah, you're right. So basically, you get a sinc in x direction because of the box function in x direction, and since the Fourier transform commutes, so you get this effect in both the directions. So that's what we get. So you have, if you see the sinc here, it has some it has a peak and then it dampens. It's the same here. So except that it happens in both directions, right? So let's say we have a dot. So probably you can't see this because it doesn't make sense. So you have an image where you have a single dot in between. So what do you expect the Fourier transform to be? Yeah. So exactly. So that's what when you take a dot image and then you take a Fourier transform, you get with a constant function. So it's important to know this, because we will revisit this when we're talking about sampling and periodization. So now let's understand what Fourier transform actually does to the images. So whenever we do Fourier transform, you basically multiply with this with this exponential with this exponential, which depends on the place where your point is, the u and v. So let's see how lower frequencies look like, which basically here when your u and v are 0, 0. So your filter is basically constant. So this is you call this as DC. So DC is which it basically captures the sum of the whole image. If just put a 0 0 in this formula, so what we end up is just double summation of the whole exponent goes to 0, and what we end up is basically the summation of all the pixels. So when we have 0 and 0, so we essentially end up with a constant which we call it, which we call as DC. So if you have 0 and 1, so 0 and 1, you give you get a filter which has a frequency along x and no frequency along y, right? So and the opposite, if you have 1 and 0, you get the opposite effect. So when you have when you pick the elements in the diagonal like 1 and 1, so you get such filters which will capture the stripes, you can say. So as we increase as we keep on increasing this u and v, we keep on getting high frequency filters. So what Fourier transform essentially says is, you can take these filters, you can take 256 times 256 times of this filter, and you can basically find coefficients which can form your image using just these filters, and those coefficients are the Fourier coefficients. So if your image has a lot of low frequencies, then mostly the coefficients will be high in the lower frequencies. Like for example, 0 0 or 0 1 or 0 0 will be always high, but I mean in the lower frequencies somewhere it will be higher. But if your image has sharp edges and a lot of edges, then mostly the higher frequencies will get excited. So so it's a really nice property which we can use it for filtering, as we see in the right now. So whenever we want high frequencies, we just we just choose the Fourier coefficients of low frequencies and then remove them, so you can end up with just high frequencies, right? So what is this? Yeah. So Fourier transform DFT 2D DFT is separable. So what do I mean by this? So okay, before that I'll tell you one more thing. So when we some terminology. So when you take Fourier when you have an image and you apply and you apply the Fourier coefficients on it, and then you end up with the Fourier transform of the image. So this part of the transform is called analysis. So basically, you are trying to see the image in a specific with respect to a specific transform. So that is the analysis. When you call it synthesis when you take this analysis and then you reapply you reapply this the Fourier coefficients back, and then you end up with the image. So this terminology is important because we'll revisit it when we're talking about patch-based denoising and all that. So this treating these two things as analysis and synthesis, we'll revisit them again in the future. So it's good to know. So what do I mean by Fourier transform is separable? So when you have a double summation, you can basically isolate y's out, and you can just consider this x. So this is nothing but so you just get a function of you can just represent this as a matrix w star, where with some abusive notation, of course, this w mean in this w, each element is it means this. Sorry, w star, each element means this, and then after that you can multiply with the same w on the other side, and you'll end up with the Fourier transform. So this is how it's implemented in the packages. So and the inverse Fourier transform is the same, except that you're now the coefficients don't have the minus in the top, right? So so yeah, let's now take an image, and we'll see the just a second. Yeah, so we'll take an image, and then we'll see how the spectrum of it looks like, right? So So we read an image. This is Barbara. So yeah. So I'll be using wait a second. Okay, yeah. So this is when you do Fft pack and Fftn, Fftn means you're applying Fft on some n-dimensional n-dimensional matrix. So you can use Fft1 if you're doing it for a signal, but Fftn is general case. So so this Fft pack I'm using it from SciPy. So you can just import from SciPy, import Fft pack, and you'll get this. So I want to. So let's just see what we have here. So yeah. So we want to see the absolute. So when you take a Fourier transform, you get the real part and the imaginary part. So the absolute value represents the spectrum. So let's see what we get. So we get a blank because the values are too high, and and then Python can't render it in a single image. So what you want, if you want to actually see how it goes, so you just add a log to it, so that you see the so that you see you're able to see the values, right? So so according to this, so you have the whenever you have so if you remember this, uh, here we had so the first value in this in this image represents how much this got how much 0 comma 0 got excited. Okay, so you see that there's high values here, and if you see so again, when we are going from top to bottom, again it's kind of repeating. So in the end, again you get when you do 256 comma 0, you again end up with low frequencies. So that's why you see this kind of structure. So here there are low frequencies, here there are again low frequencies, here and here. So so it's kind of tough when you it's kind of I mean it's just a matter of convenience, but we prefer all the similar frequencies to be at the same place. So it's a norm like used everywhere in MATLAB, Python, everywhere. So you have this function called Fft Shift, so which basically just swaps the quadrants. So your fourth quadrant is basically swapped by the second quadrant, and also the same with 1 and 3. So when you shift it, you get something like this, right? So in the center it's the high frequencies, and as you move away it's the low frequencies. Okay, in this image if you see this has Barbara has a lot of stripes. Just a second. I don't know the command how to increase the size, so you have to bear with me for that. So so yeah, so Barbara has a lot of high frequencies in these areas, on the stripes, on the scarf, and on the table and all that. So that's why you see a lot of these things getting excited. I know it doesn't make sense on the first go, but if you see a smooth image, then you'll get what I mean. So so now we'll look at another image. I'll come back to this. So now we'll take another image and we'll see the Fourier transform. So by the way, and all these images are grayscale. Just you can change the color map to gray and you can see the actual images. They're not blue or anything. So if you observe in this image, you see this kind of pattern, right? And so this is kind of, you're seeing it's periodized it's looking kind of periodized. It's repeating itself. So since this image has a lot of repeating patterns, so what Fourier transform thinks is so you have many repeating patterns within this image. So that's why you get these Fourier elements get excited at several frequencies. So that's why you see this kind of pattern. And let's see another smooth image. Sorry. Also excess. Uh, I'm not sure. I can see actually both of them. I mean, it's squares, right? They're just tiles, so I don't know. It's tough to read into this Fourier images. It doesn't mean anything, and we'll see why that they don't mean anything. So this is relatively smoother. So you don't see any edges. It's just smoke. So there's no strong reflector. So most of the now if we compare this to this, you see that all these high frequencies they belong to they belong to the scarves and all these things. So we'll exactly see what they mean. But if what I wanted to say was, if you take a smoother image, then only the spatial only the center ones get excited. So yeah, so now we'll understand two different things, like what amplitude means. When you take a Fourier transform, you get real and imaginary parts, right? So which basically means you get an amplitude and a phase of a complex number. So we'll see what each of these things mean. Okay. So yeah, first what we're seeing is we're loading a picture of Lena. So let's show that also.
Pictures are from the packaging?
No, I just downloaded from the web and I uploaded all the required pictures to the Git. So so this is the original picture, and now so let's see so what we're doing here is just what I explained just a while ago. So we're taking the Fourier transform and then we're taking the absolute, and since we can't really read into it, so we're taking a log so that it's just more visible. Just note that when you're doing any filtering on the Fourier transform, you shouldn't do it on the log. You should do it without the log. Log is just for visualization sake. So so this is the image of Lena, and this is its amplitude, and now we'll see what the phase is. So the phase is basically when you have a complex number. What is a phase? If you complex number is a e power I theta, right? So a is the amplitude that we saw, and theta is basically basically when you have a complex number and you ask a numpy, so it just takes tan inverse complex by real part, and that is the theta. So which is what we call as phase. So we see what phase is. So this is the phase of Lena, but it doesn't look like anything. So it just like it seems like noise, but we see that this is the most important part in the image, and this is not useful at all. So let's reconstruct Lena from just the phase, right? Okay, let's first reconstruct. Let's first form a complex number. So amplitude times e power I theta. So basically, this is what the Fourier transform is. And now we'll do an IFFT inverse Fourier transform, and then we'll get the real image, right? So I'm doing an abs here just because when Fourier transform, when you do an IFFT, you have some parts of since it's not to the point accurate, it's just an approximate one. So it still produces a complex number, but you can either you can either just check the real version of the output or just take the abs of it. So I'm doing just the abs. So this is the I'm just combining these two, and I can see that I can reconstruct the Lena back, right? So the Fourier transform is fine. So now I remove the amplitude, and I just reconstruct using the phase. Okay. So let's see what we get. This is what we get when we reconstruct just using the phase. So you see that it's, although the phase looks like nothing, it still captures a lot of information, and you can still see that it's Lena, right? So let's do it just with the amplitudes. So I just did the same thing, and again I used log for visualization. So basically I did inverse Fourier transform of amplitude, uh, and then just viewed it, right? So this is what you get when you see the amplitude. It just means nothing. You don't see any structure. So basically, when you take a Fourier transform, the most of the information is captured in the phase, and and not in the amplitude. So let's see one more example. We'll take two images, Lena and Barbara. So, and what we do is we'll just combine the phase of one image to the other image, and we'll just swap both of them. So, and we'll see what we get, right? So I took two images. I calculated the amplitude of them and phase of them, and then I'm reconstructing the first image back by using the amplitude of second image, and vice versa. So second image with the amplitude of first image, and the phase, right? So then so you see the first for the first I'm doing a sanity check, and first image with the amplitude of second image looks almost, since we retain the phase and we just change the amplitude, it still looks like Lena. And this is the Barbara image with Lena's amplitude. You see that it still remains. So phase is really important. And yeah. So yeah, let's now do some filtering in the Fourier domain. So what do I mean by that? So when we have the spectrogram image, or this amplitude image, in the center we have low frequencies, and in the far away we have high frequencies. So let's if we can let's do some filtering and see if we can get high low pass filters and high pass filters from it. So yeah, so I'm loading an image again, and then I'm taking a Fourier transform and shifting it so that I get all the high frequencies in the center, and I'm just showing it to you. So yeah, I want to create a high pass filter. Yeah, and high frequencies are far away. In this image, but not in the actual Fourier transform. Yeah. So I want to create a high pass filter, which basically it doesn't allow any of this any of the frequencies in this block while you're forming the image. It just passes the high frequencies. That's why it's called high pass, right? So I'm creating kind of a box and putting zeros in it, and I want to see how it looks like. So this is my low pass filter, and sorry, high pass filter. So let's see. I'm just doing an inverse Fft of it and seeing what it captures. So when you remove all these stuff, and you're just and you're remaining with all the rest, so you see that it captures all the very sharp details that you need. I mean, it's capturing. It kind of looks like what we saw in the last class with the Laplace convolution. So it's kind of it is high pass filter. It's just passing the high frequency content, and this is with, yeah. Otherwise you won't get anything useful, right? Yeah. So yeah. So now let's create a low pass filter and see what we get. It's the same block basically. So instead of passing, I'm creating a mask where it passes only the ones in the center and it zeros the rest. So basically this is the mask and this is my filtered Fourier transform, and then I reconstruct back the image. So you see that it lost all the details, but the high level features are still fine, except you see the fabric is it's white. It doesn't capture any high frequencies, and image has a lot of artifacts. So this is low pass. This is the high pass. This is the low pass filter. So you're passing only the low frequencies, right? So you see three of the images. So image, low pass filter, and high pass filter. So so there's this very important problem in image processing. It's called super resolution. So what super resolution, the problem posed by super resolution is you're given this kind of image and you want to recover this, right? So basically you have to create these edges out of nothing. So it's a really, this problem is realistic, because when you have cameras with a PSF which is kind of modified, and it creates if it creates kind of a blur, so it's kind of similar to cutting down the high frequencies. So if you have some shakes in the camera, or when if your PSF is not, if you're not focused enough, so you get images with no high frequencies and you want to recover them. So we'll see in the future, in towards the end of the course or something, how do we recover these high frequencies from this good quality image from a blurred image. So yeah, that's it. So I uploaded the code onto GitHub repository of the class, so you can just download and run it for yourself. I added very detailed comments, so it will be, I mean, I think it'll be just you can just run it in 1 hour or something, and that's it. Thanks.